Good morning. Assalamualaikum warahmatullah. We continue with lecture 13 of CHM477, and today I'm going to cover structure of coordination compounds. In my previous lecture, we completed the topic of naming of coordination compounds or nomenclature. Okay, now we go into the structure of coordination compounds. Sometimes when we're studying the geometry of coordination compounds, we find that there is more than one way to arrange ligands around the central metal atom. Compounds rearranged in different fashions have distinctly different physical and chemical properties. For commonly encountered coordination compounds, there are four geometric arrangements. It's common for you to find linear arrangement where you have one metal attached to two ligands, so you get a linear. You are also familiar with tetrahedral geometry where one metal is attached to four ligands in the four corners of the tetrahedron. And sometimes these four ligands arrange themselves in square planar. There's going to be some difference in terms of angles, and obviously there will be a few metal centers that are inclined to have square planar arrangement, and a few prefer to have tetrahedral arrangement. And last but not least, you have the good old octahedral geometry, where the metal is surrounded by six ligands at the six corners of the octahedron. Now, the coordination number of this metal, M here, is 2 because it is attached to two donor atoms. The coordination number of the metal in tetrahedral Cn, coordination number is 4. Here is the coordination number is 4 as well because there are 4 donor atoms around the metal center. And for octahedral, the coordination number is 6. Okay. Now in the diagrams above, let me make that smaller in one page. In the diagrams above, you see that the structure and coordination number of metal atom relate to each other as follows. When the coordination number is 2, you get a linear structure. When coordination number is 4, you get either tetrahedral or square planar structure. But if the coordination number is 6, you get octahedral geometry or octahedral structure. Now that is the common thing about structures of coordination compounds. Now I'm going to talk about isomerism. Now isomerism arises for compounds that have the same chemical formula. Well, you know this, isomers have the same chemical formula, but they have different arrangement. The atoms are arranged differently and giving rise to different physical and chemical properties. One isomer, even though it has the same formula, chemical formula as another isomer, usually isomers will have very, very different chemical and physical properties. The most common and the most important type of isomerism in coordination compounds, there are two types. One is constitutional or sometimes called structural isomerism. The other one is called stereoisomerism. Now let's see what are the differences between structural isomerism and stereoisomerism. Well, we all know isomers have the same chemical formula but different properties. The constitutional or structural isomers happen when atoms connect differently. When atoms connect differently. Now, and stereoisomers occur when there is a different arrangement in space, different spatial arrangement. Now, an example of constitutional or structural isomers, there are two types, further broken into two. The first is called the coordination isomers, and the second, linkage isomers. In coordination isomers, the ligand and the counter ion undergo an exchange. I'm going to explain to you with example later. Whereas in linkage isomer, the same ligand but having different donor atoms. Whereas for stereoisomers, where there is a different arrangement in space, you have geometric isomers, cis-trans, giving rise to diastereomers, and optical isomers, giving rise to enantiomers. Now, different arrangement for geometric or cis-trans isomers, there is a different arrangement around the metal ion, whereas for optical isomers, there is non-superimposable mirror images. Now, this may not be making a lot of sense to you now, but as we go through each type one by one, you will be able to see clearly. Now, often these isomers appear to have very, very striking physical differences. Maybe they have different colors, maybe they have melting points, despite the fact that they have the same molecular formula. Now, let's go through the first type, which is this family, which is the constitutional or structural isomers made up of coordination isomers and linkage isomers. Let's go through each one with examples to make things clearer for you. Now, constitutional isomers is when there are the same atoms, when they have the same atoms, but the atoms are connected differently. Now, two compounds with the same formula, but the atoms connected differently, they are called structural or constitutional isomers. Now, coordination compounds exhibit the following two types of constitutional isomers. One involves a difference in the composition of the complex ion, and the second involves a difference in the donor atom of the ligand. Okay, let's see what is this one first, about the coordination isomer. Yep, let's have a look at here. Coordination isomer is when ligand and counter ion undergo exchange. Now, let's see. Now, coordination isomers occur when composition of complex ion changes, but not that of the compound. The compound remains the same, but the composition of the complex ion, the species in the bracket, in the square bracket. One type of this isomerism occurs is when ligand and counter ion exchange positions. Now, let's have a look at this. In the first molecule or in the first compound, you have this situation where platinum has 4 ammonia ligands attached to it and 2 chloro ligands attached to it, and the whole complex ion has a charge of +2. Yeah, +2. So this must be platinum 4. And NO2 minus or nitrate act as a counter ion, as counter ions to neutralize the charge of this complex ion. That's one. But in another compound, the chloro and the nitro may exchange place. Yeah? May exchange place where chloro becomes the counter ion and NO2 become the ligand. So when you have this and that happening, yeah, when you have these two exchanging place, then you call that coordination isomerism. These two are coordination isomers. Yeah, that's clear. Now in the first compound, this one here, the Cl minus ions are the ligand and the NO2 minus ions are counter ions. But in the second compound, the roles are reversed. Now there is another way, so that is the first way. There is another way that this type of isomerism occurs in compounds of two complex ions in which the two sets of ligands in one compound are reversed of the other. So this is another example. In the first example, you have chromium attached to 6 ammonia to make one positively charged complex ion. And then that complex ion is having a counter ion of another complex ion, which is cobalt, attached to 6 cyano. So this second complex ion that I'm highlighting has a charge of -3, whereas this first complex ion has a charge of +3. So remember, chromium attached to amine, cobalt attached to cyanide. But that can exchange place in the second isomer, another coordination isomer, where cobalt now is attached to 6 ammonia and chromium attached to 6 cyano. Yeah. So these two, the ones that I highlighted, yeah, these two compounds, yeah, each compound having two complex ions, these two compounds are coordination isomers. Yeah. Note that ammonia is a ligand of chromium 3+ in one compound, and it becomes a ligand of cobalt 3+ in the other compound. So those are two examples of coordination isomers where you have ligand and counter ion exchanging. Yep. The second type of constitutional or structural isomerism is linkage isomers, where different donor atom. You have the same ligand but different donor atoms. And linkage isomers occur when composition of complex ion remains the same, but the attachment of ligand donor atom changes. So how is that happening? Now, some ligands can bind to metal through either one or either of the two donor atoms. For example, the nitrite ion can bind through a lone pair on either nitrogen. When it does that, we call it nitro, or oxygen. When it does that, we call it nitrito. So NO2 can either bind through oxygen or it can bind through nitrogen. When it binds through nitrogen, you call that nitro. When it binds through oxygen, you call it nitrito. And this will give two different compounds that are linkage isomers, as in the orange compound. So this one here, the orange compound here, pentaamine nitro-cobalt 3 chloride, yeah, pentaamine nitro-cobalt 3 chloride. It has a light orange color. So this blue thing is nitrogen. It is attached to that cobalt center. So it is attached through nitrogen. It's called nitro. But the same ligand, NO2, can attach through the oxygen like this. This is the oxygen. And this is called a nitrito. This is called pentaamine nitrito cobalt 3 chloride. Yep. And the ligand NO2 is no longer NO2. It is ONO now because ONO. Otherwise, it's NO2. Yeah. And the compound that is produced when this NOO attached through oxygen is distinctly different from this compound. Even through the color, you can see the difference. One is light orange, one is darker orange. So these are two very, very different compounds to each other, but they have exactly the same formula, they have exactly the same ligand, but the ligands have different points of attachment. Yes, and that is called a linkage isomerism. Yeah. Another examples are when you have a cyanate ion, which can either attach through the oxygen, which is that ligand will be called cyanato, yeah, oxygen, NC, or there is the lone pair of electron on the oxygen that's getting attached, or it can also attach through the nitrogen atom, which people then call it isocyanato. Isocyanato. So when it attached through oxygen, the name becomes cyanato. When it attached through nitrogen, it becomes called isocyanato. The thiocyanate ion, this is the thiocyanate ion, it can also be donating the lone pair on sulfur, or through nitrogen. So when you have it's donating through sulfur, the compound is different. When it donates through nitrogen, it is called thioisocyanate. Yeah. So you have NO2 doing the same linkage isomerism. Cyanate also can perform linkage isomerism. Thiocyanate also can do the same, doing attachment through different donor atoms in the same ligand. So those are examples of linkage isomers. So we have covered the constitutional or structural isomerism, coordination isomers, and linkage isomers. Now we are going to go into stereoisomers next, where there is a different arrangement in space. It's not about now the differences in atomic connection, but now the difference is in the arrangement in space. You can have either cis trans or optical isomers. So let's go through that. Now, stereoisomers are when you have different spatial arrangements of atoms, different arrangement in space of atom. Stereoisomers are compounds that have the same atomic connections but different spatial arrangements of the atoms. They are made up of the same type and numbers of atoms bonded together in the same sequence but with different arrangement in space. There are two types of stereoisomers. One type is called geometric isomers, which is usually known as the cis trans. The second one is called the optical isomers. And this optical isomers is slightly more involved. But never mind, we'll go through that one by one. Now, coordination compounds may exhibit one or both types of isomerism. Note, however, that many coordination compounds do not have stereoisomers. You'll see why. Now, we go through the easier example or the easier type to understand, which is the geometric isomers. Cis and trans. Cis is side by side, trans is across one another. Yeah. Now, geometric isomers are stereoisomers that cannot be interconverted without breaking any chemical bond. When you want to convert isomer A to isomer B, you cannot do that unless you break some bonds. So that is geometric isomers. Geometric isomers usually come in pairs. We use the term cis and trans to distinguish one geometric isomer of a compound from the other. Cis means that two particular atoms or group of atoms are adjacent to one another or next to each other. And trans means that the atoms are opposite side in the structural formula. Now have a look at this example here. The pink and the green compounds are exactly having the same chemical formula. Yeah, it is tetraamine dichloro cobalt 3 chloride. So let's do that here. So you have cobalt having 4 ammonia, tetraamine dichloro 2 chloro. That is in square bracket to indicate that it is complex ion. Yep. And there is chloride outside. Now, can you tell me how many chloride will this be? How do you determine how many chloride will there be? You just have to look at what is the charge of this complex ion. Yeah? You know it is cobalt 3. So 3, 0, 2 minus. So this must be 1 plus. Yep. The complex ion must have a charge of 1 plus. That means there is only one chloride to counter that charge. So there is only one chloride to counter the charge because this is cobalt 3. So tetraamine cobalt 3 chloride. No. Tetraamine dichloro cobalt 3 chloride. Yeah. But when you have the chloro cis to one another, the compound appears pink. But when the 2 chloro is trans to one another, this is the compound, it appears green. So this is a cis arrangement of chloro ligand. This here has a trans arrangement of a chloro ligand. Yep. So you can see very well that you can see very clearly that having different arrangements or different positions of your chloro, either cis or trans, will give you very, very different appearance of compound. One is pink, cis, one is green, trans. Yep. This is another one. This is another one. You have cis and trans isomers of diamine dichloroplatinum 2. You have platinum 2 here. You can have the 2 amine cis to one another and chloro cis to one another, or you can have the 2 amine trans to one another and the chloro trans to one another. Now this is called, A is called cis and B is called trans. Yeah? This is cis, this is trans. Trans isomers of diamine dichloroplatinum 2. Note that the 2 chloro atoms are adjacent to one another in the cis isomer and diagonal across each other in the trans isomer. Now, these two compounds have very, very different biological properties. This one is called a cis dichloropplatinum or diamine dichloropplatinum, and the common name for it is called cisplatin. cisplatin. This is a transplatin. Now, cisplatin is a very, very good cancer-killing agent. It can kill cancer cells because of the position of this ammonia. But if you change the position of this ammonia to become trans to one another, this compound cannot kill cancer cell. This is a very, very strong anti-cancer agent. This has no effect, none whatsoever, on cancer cells. Yeah. So cisplatin is a good anti-cancer agent. Transplatin has no anti-cancer properties. Now, note that although the types of bonds are the same in both isomers, there are 2 PTN and there are 2 PTCl, the spatial arrangements are different. Yep. Now, another example is here. Here you have your chloro cis to one another. Here you have the chloro trans to one another. Here you have the chloro cis to one another, and here you have the chloro trans to one another. Now, the A and B, the A is the cis and B is the trans isomer of tetraamine dichlorocobalt 3 ion, and C can be generated by rotating A. When you rotate A, you make C. Can you see that? If you make this going to the top, that means you are making this going to this top here, you are going to have C. And D can be generated when you rotate B. So when you rotate chloro into this position, this chloro will go down here. This is the structure that you're going to get. So A is actually C, B is actually D. Yeah? And you cannot interconvert between A and B. When you requested to, I don't know if you are, when you want to change A into B, you cannot do that at all unless you break some bonds. Yeah? Unless you break some bonds, you cannot exchange compound A into compound B. So these two are definitely two different compounds. But A can be made into C, so they are the same compound. B can be made into D, and they are the same compound. Yeah. So that is explanation about geometric isomers. Now I'm leaving the most fascinating isomer to the last, which is called the optical isomers. Now optical isomers, yep, if you look into this, I'm going back, way back. Here, I've explained to you coordination isomers, linkage isomers, geometric isomers, and optical isomers. Optical isomers have enantiomers, whereas geometric isomers have diastereomers. So what do I mean by that? So these two are diastereomers to each other. A is diastereomer of B, and B is diastereomer of A. A and C are the same, B and D are the same. So these are diastereomers. Yeah, diastereomers. But when we go into optical isomerism, now optical isomers are non-superimposable mirror images. When you have a compound, yeah, here is a compound, for example, in this arrangement, and you have a mirror image of it. Can you see that both my hands are mirror images? Yep. If there is a mirror between this, well, unless I change the position of my ring. Yep. Now, mirror images. Yeah, can you see? If the two mirror images are not superimposable, then these two are called optical isomers. But my hands, I cannot superimpose them because if this is facing, this is my left hand. My left hand and my right hand are facing you, right? They are mirror images to one another. Agree with me? While facing you, still I am not changing the orientation of these two. I cannot superimpose them. Yep, I cannot superimpose. My thumb is on top of my little finger, whereas this time at the back is on top of my little finger. The only thing that can be in the same position is my middle finger. So my two hands are non-superimposable mirror images. Can you try with your hands? Are your hands non-superimposable mirror images? Of course they are. If your hands are superimposable mirror images, then you are not the same as me. You're not the same species, but never mind. So my hands are non-superimposable mirror images. So that's what is meant by non-superimposable mirror images. Now, superimposable means that if one structure is laid over the other, the position of all atoms will match 100%. But as you can see, my hands are not. My hands are not superimposable. Yeah. So by definition, my hands are optical isomers. Yeah. Like geometric isomers, optical isomers come in pairs. Yeah. Like geometric isomers here, you have your cis and your trans. These are a pair of diastereomers. My hands are a pair of enantiomers. This is one enantiomer. This is another enantiomer. Now, however, the optical isomers of a compound have identical physical and chemical properties. They have the same melting point, they have the same boiling point, they have the same dipole moment, they have the same chemical reactivity towards molecules, and they are not optical isomers themselves. Optical isomers differ from each other in their interaction with plane polarized light. Yeah? Optical isomers of a compound have identical physical and chemical properties. When they have identical, they are not optical isomers, okay? Now, the structural relationship between two optical isomers is analogous to the relationship between your left and right hands. If you place your left hand in front of a mirror, the image that you see will look like your right hand, as I showed you earlier. We say that your left hand and your right hand are mirror images of each other. However, they are not superimposable because when you place your left hand over your right hand with both palm facing the same way or the up or down, they do not match. Yeah. So this one in the mirror is your left hand. This one in the mirror, outside of the mirror is the left hand. The one inside looks like your right hand, but you cannot superimpose them if they are facing the same way. Yeah. So here is example of a molecule that match that description. You have cobalt with two ethylene diamine. This is N, so that's ethylene diamine. That's another ethylene diamine, which is a bidentate ligand, and 2-chloro. When you put a mirror between them, you are going to have this molecule. Yeah. So the A, which is cis, this is cis, and B, which is trans isomer of dichloro bis ethylene diamine cobalt 3. So you have dichloro bis ethylene diamine cobalt 3 ion and their mirror images. Now, if you could rotate the mirror image in B, which is this one here, the mirror image in B, 90 degrees clockwise about the vertical position. Now, this is when I really wish I could be in front of you. Yeah. If you could rotate this about this vertical position, you are going to have this chloro going there and this chloro going here. Correct? And place the ion over the trans isomer, which is this one here, you will find that the two are totally superimposable. When you turn this into there, and this obviously come into here, you take this molecule and put it on top of that molecule, you will find that they are totally matching. You can put one, obviously the cobalt will be on top of cobalt, this chloro will be on top of that chloro, this chloro will be on top of that chloro, this chloro will be on top of that chloro. And remember, this nitrogen is closer to you. Yeah, no. This nitrogen is to the back of the paper. This nitrogen is to the top, so this nitrogen will still be at the top when you rotate this, but that will be going to, this is going to 100, yeah, this is going 180 degrees like that. Yep. I really wish I had you in front of me with a chemical model. Just believe me, when you rotate this 180 degrees, put it on top of that, you will definitely have a good match, i.e., it will be exactly the same compound. Yep. However, no matter how you rotate your cis isomer, this one is your cis isomer and its mirror image, you cannot superimpose one from another. Now let's try and rotate this into here, and that become, you'd rotate that 180 degrees, yeah? This will be rotated 180 degrees, this will be rotated 180 degrees. You cannot take this rotated molecule and put it on top of this one. You cannot have them matching. I'll try to find a video for you to watch about this. I think it's better for you to go and find a video in YouTube about optical isomerism and how these two cannot be superimposed to one another. Then you will understand this topic better. Yeah? Figure 22.13 shows the cis and trans isomers of this compound. Careful examination reveals that the trans isomers and its mirror images are superimposable, but the cis isomer and its mirror images are not. Therefore, the cis isomer and its mirror images are called optical isomers. So when you cannot superimpose the mirror image of the molecule with itself, then these two are called optical isomers. But these two, because you can superimpose them, they are not optical isomers. Yep, the trans are not optical isomers, but the cis are optical isomers, and these are called enantiomers. Yeah, enantiomers cannot be superimposed with one another. Yep. Optical isomers are described as chiral from the Greek word of hand because, like your left and right hands, chiral molecules are non-superimposable. Isomers that are superimposable with their mirror images are said to be achiral. So this one that you can superimpose, we call this a chiral molecule. These two are chiral molecules. This one chiral because you cannot superimpose them. These two are chiral because you can superimpose them. Yeah. Chiral molecules play a vital role in enzyme reactions in biological systems. Many drug molecules are chiral. It is interesting to note that frequently only one of the pair of chiral isomers are biologically effective. Now, chiral molecules are said to be optically active because of their ability to rotate the plane of polarized light as it passes through them. Unlike ordinary light, which vibrates in all directions, plane polarized light vibrates only in a single plane. Now, we use polarimeter to measure the rotation of polarized light by optical isomers, which I'm going to show you down here. A beam of unpolarized light passes through a polarized sheet called polarizer, and then through a sample of tube containing a solution of optically active chiral compound. As the polarized light passes through the sample tube, its plane of polarization is rotated either to the right or to the left. This rotation can be measured directly by turning the analyzer in the appropriate direction until minimal light transmission is achieved. Now, if the plane of polarization is rotated to the right, then that isomer is called dextrorotary, D. But if the plane of rotation is rotated to the left, then you call it levorotary. So dextrorotary for isomer that rotates light to the right, whereas levorotary is the isomer that rotates light to the left. D for dextrorotary, L for levorotary. The D and L isomers of a chiral substance are called enantiomers. Always rotate the light by the same amount. If D isomer rotates the light to the right by 30 degrees, the L isomer will rotate it by 30 degrees to the left. So you have the same degree of rotation by D and L. So when you mix the same amount of D and L isomer in one solution, you do not see any rotation because anything that's rotated to the right will be rotated back to the left in the same magnitude. So the net rotation is 0. And that mixture, when you have the same amount of D with L isomer, is called the racemic mixture. Yep. So here, let me explain what I have just read to you in that thing through this picture. Now, this is your light source. Light source will vibrate in all sorts of directions, to the top, to the bottom, to the left, to the right, in every direction. When it passes through a polarizer, this is a polarizer which only allows light of one direction to pass. The other directions will be filtered out. Only the one having the same direction as the polarizer will pass. So you're going to have only this light component passing through. Yeah. When you have levorotary, yeah, levorotary isomer in here, this plane polarized light will be rotated to the left. When you have a dextrorotary in here, it's going to be rotated to the right. So you can see that this optically active substance in the solution is rotating, the light, it enters the solution at vertical position, it goes through the solution being rotated, and it exits the solution being horizontal, for example. So there is rotation happening. So chiral molecules can rotate plane polarized light. So if you want to test for chirality, you put your solution into this, and if your plane of polarized light is rotated, that you know it is a chiral molecule. If it doesn't get rotated, then it is not chiral molecule. It is chiral when the mirror images are non-superimposable. It is not chiral when the mirror images are superimposable. Yep. I hope you understand that lecture. Yeah, it is quite involved, especially when you have come to the optical isomers. But go through my notes and then listen back to the parts that you're confused about. And if you have any problem, you can still ask me questions. So that's it for now. I'm going to stop here for my lecture 13. I'll see you in my lecture 14. Okay then, Assalamualaikum. Bye.